And this is tutorial number 2, right? So here the first question, for the network shown in figure Q1 with respect to terminals A and B, right? So these are the two terminals. Okay, so using two loop currents, right, determine the current flowing through R4. Okay, so you have to determine the current flowing through R4, which is 10 ohm resistor. Okay, so then you have to calculate the Thevenin equivalent resistance RTH, right? Then calculate the Thevenin equivalent voltage VTH, and hence determine the Thevenin equivalent circuit. So when we calculate RTH and VTH, we can find the Thevenin equivalent circuit. Okay, so this is the circuit. So these are the two places, right? So between this we have to derive our circuit, and first we will apply two loop currents, right? So here, as you can see, let's mark the current going in here as I1, and the current going here as I2, and the current in here as I3, right? So if you apply KVL to this one, right, here if you apply for A, B, E, F, right? So this A and this B, this A and this B, they are different, right? So therefore you can see here this voltage 10 volts, that is equal to here the voltage drop through this one is 8 I1, right, and the voltage drop in here is 25 I2, right? So therefore 10 is equal to 8 I1 plus 25 I2, right? So that is equation 1, right? Then for BCDE, if we apply BCDE means B, C, D, E, right? So if you apply KVL in here, so you can see the 8 volts will apply like this. Then here the current is I3, therefore the voltage will be 4 I3, and here the voltage will be 10 I3, and since the current is going downwards, the voltage in here, voltage drop in here is 25 I2, right? So if we can either write 25 I2 plus 8 equal 4 I3 plus 10 I3, or else we can write it as 80 equal 4 I3 plus 10 I3 minus 25 I2, right? So 4 I3 plus 10 I3 minus 25 I2, and then we can obtain the second equation, right? So after obtaining the second equation, we can solve we can solve by knowing that I1 is I2 plus I3. So by applying KCL at B, right? KCL at B, because here the current coming in here is I1, and the current going out of this node is I3 and I2, right? So therefore I1 is equal to I2 plus I3. So solving this one and this one, and question number 3, right? So we can obtain I1 equal 0.891 and I2 equal 0.114 and I3 equal 0.7764, right? So so those currents, right? So here we have obtained this one, this current, and this current, right? So using two loops, determine the current flowing through R4, right? So you know that this is I3, right? I3, and that I3 current, it will not go in this direction. Why? Because here it is open circuited, there's no path, so therefore the total I3 will go through this one. So therefore I3 is the current that is going through R4 resistor. Okay, so that means this value, it is the current going through R4 resistor, right? So then okay, so like this we can write. Then calculate the Thevenin equivalent resistance RTH, right? So in order to calculate the Thevenin equivalent resistance, you know that first of all you have to, right, first of all so you are obtaining the resistance between A and B. So therefore first of all you have to short circuit all the voltage sources. So if you short circuit this, it's like this. So here there's no voltage, so therefore the resistance 8 and 25, so they are in parallel. So therefore in here you can have R1 parallel R2, right? So we don't have these two, right? Then with that R1 parallel R2 we have R3 in series, right? So therefore actually RTH is equal to R3 plus R1 parallel with R2, right? And the total thing, it is in parallel with this, which is R4, right? So if you calculate that value, right, in here you will get something like 20 ohms, right? I will get it as 20 ohms. Then so we have finished this one. So I'm going to calculate the Thevenin equivalent voltage VTH, right? So how to calculate the Thevenin equivalence voltage? So it's simple as that. Thevenin equivalent voltage is actually the voltage that is present between here and here, right? So previously we have determined the current going through this one is 776 milliamperes, right? So therefore actually what is the voltage that is between A and B? That voltage is equal to 776 milliamperes multiplied by 10, which is equal to 7.76 volts, right? So this is VTH, right? So we have found RTH and VTH, okay, RTH and VTH. Then in Thevenins, you know, the voltage source and the resistance, they are in series, so therefore we have this configuration: VTH 7.76, RTH it is 20 ohms. So that means the total circuit in here we can replace by that, okay. So VTH RTH, right? So here these are A and B, right? Therefore we have calculated these, and so if there is like load connected, like, so there's you can see there's no load, right? So if there's something, a load is connected, in order to find the Thevenin's equivalent you have to remove the load, right? You have to remove the load, then you, for the rest of the circuit, after removing the load, for the rest of the circuit you have to calculate the Thevenin's equivalent, okay. Then we'll go to question number 2. calculate the current flowing through the 10 ohm resistor shown in figure Q2 using Thevenin's theorem, right? So in order to do this, we will do like a few more theorems along with the Thevenin's theorem, right? So if we take a look at this is the circuit that we have, right? So this is 6 volts, 4 volts, 2 ohms, 3 ohms, right? And this is 10 ohms, right? So this is 10 ohm. So you asked to calculate the current flowing through 10 ohm resistor shown in figure using Thevenin's theorem, right? So in order to, so now can you see that now this 10 ohms it is becoming like a load, right? It is becoming like a load. So therefore we have to remove this part from the circuit, then the rest, that means this one, this part we have to represent as a Thevenin's equivalent. So after representing that, we can connect RTH VTH to this 10 ohm resistor, right? So now we are going to find this RTH and VTH, right? So I will show you how to do it. So here like this we will separate it, right? Then then you know that you know that when you have like something like this, right? Voltage in series with a resistance, right? So this is actually equal to a current source, right, with resistor in parallel, right? So the resistance in here will be the same in here, and the current value, this current I, that value will be equal to V divided by R, right? V divided by R. So therefore for this one, right, this one I can replace it like this, right? Current source which has 6/2, right, and resistance is 2, right? Then here that is connected with this one, right? So therefore 4 volts and 3 ohms on, that is again I can represent like this, right? Okay, can represent it like this. Okay, so yeah, this is right. We can represent it like this. So now this is 6/2, this is 2, 4/3, so these are currents, right? So these are current because this is how we represent the current source, and here 2 ohms and 3 ohms, right? So you may know the Millman's theorem. Millman's theorem means, so when you have like the current source, current sources and resistors in parallel, right? Resistors in parallel, for this each resistor, right? For this each resistor, right? If I represent this by the conductance, what is conductance means? It is 1/2, right? So the 1/2, so 2 ohms means conductance 1/2, right? And this 3 is conductance is 1/3, right? So according to okay, you can see here, this is the Millman's theorem, right? Millman's theorem. So when you have current sources I1, I2, I like that with the G1 G2 the conductance in parallel, right? We can represent it as current I and G, and this I value is the addition of all the currents. I is I1 plus I2 plus I3 plus up to IN, right? And this conductance is addition of all the conductance, so G1 plus G2 plus G3, right? So if we apply that on here, right? So what is the total current? What is the total current I? That will be 6/2 plus 4/3, right? So 3 plus 4/3, right? That will be 13/3 amps, right? And what is the conductance G? Conductance G is again the addition, right? 1/2 plus 1/3, so 5/6. So this is 5/6. Okay, this is 5/6. This value is 5/6, right? So then if we are converting, right? So the same thing we can represent it as, right? We can represent it as this voltage. So here we have this configuration, right? So the configuration that is given in above, we can represent it as like this, according to the Millman's theorem. 1/G is the resistance and I/G is the voltage, right? So okay, so this is actually G, right? This is G and this is I, right? So therefore here this is the voltage and this is the R, right? So what is R actually? R is 1/G. So what is 1/G? Here the one that I have written here, it is correct, right? So I am just showing you how to count it using the conductor. So the resistance is correct. Resistance is 6/5, right? Conductance is another representation, right? But I will go with that one, right? So therefore 1/G means resistance is equal to what? 6/5, because G is 5/6, resistance is 6/5. And what is V? What is V equal to? V is equal to, according to this, 1 I/G, right? So I is over G. G means 5/6. So 3 2 will cancel out, so 26/5, right? So now here this is resistance in ohms and this is VTH in volts, right? 26/5. So what we were asked to find, you asked to find the current flowing through the 10 ohm resistor, right? That means here. So now so we have removed it now. Here can you see the same thing that we got, right? Same thing that we have got. Okay, so now I will connect that 10 ohm resistor like this. So this is okay. So the current going in here, let's say it is I or ITH, so the same current will go through because these signs is, so 26/5 equal ITH into 6/5 plus 10, right? So therefore if you simplify, you will get the answer as 0.4642. Okay, 0.4642, that is the current going through this 10 ohm resistor. Okay, Then the next one, question number 3, calculate the current flowing through the 10 ohm resistor shown in figure Q3 using Norton's theorem and superposition theorem, right? Okay, Thevenin analysis means like you have done this previously. Okay, so right, so how can we do this again? Again we can do the same thing, but first we will consider superposition, right? So in superposition we will consider what you have to find through this one, right? Okay. Okay, so in superposition what we are doing is we will consider one source for each circuit, then we will add all of them together, right? So here here we have this is 6 volts, so 2 ohms, right? In here, right, we can apply we can find this Ix, right? So how to find this Ix? How to find this Ix? Here 3 and 10, they are in parallel, right? So therefore without 3 and 10 we can represent the resistance which is parallel, so which is equal to 13 over 13, right? So what is Ix as it marks in here? It should be 6 volts divided by the total resistance, which is 6 divided by, so you will get this answer, right? So we know this, so then we can apply the current divider, right? So current divider means the current going in here, right? So we'll just erase this now, right? In current divider what you have to do is, so here this is the current in here Ix, right? Ix, that will be divided to I1 and I2 proportional to the resistance of the other branch, right? So that means current going in here I1, that is proportional to 10 divided by 10 plus 3, that means 10 divided by 13, so this much. So this is Ix into 3 over 13, that is equal to I2, because so I1 it is 1.3928 into 10 divided by 13, right? Okay, like that. So you will get that value. So actually we don't need I1, right? I1, we need I2, right? So I2, we got this value, right? Then here we will mark with the next circuit. So there can be two circuits, right? Because we have only two sources. So this is 4 volts, and here this current is Iy 2 ohms, 3 ohms, and here this is I2, right? So again, right, again we can calculate directly, we can calculate I current in here, right? So I think that here must think so using the previous one also we can calculate like this. So I will show you that. So here like this we have 4 volts, and if we can draw, if you want it like this, right? So here this is 3, and here this is 2, here this is 10. So 2 into 10 is 20 divided by 12, right? So the current in here, let's say this is I dash or something, I dash, you can find it as 3 divided by 3 divided by the resistance, the equivalent resistance will be sorry 4 divided by, right, the voltage is 4, 3 plus 20 over 12. Like this we can calculate I dash, right, I dash. Then we can calculate this I2, right, we can calculate I2, right. So you will get I2 as 0.1422, right, 1422. We are doing this one, right, 422, right. Then using the superposition theorem, what we have to do is we have to add both currents together, the current found in this occasion and the current found in the previous occasion, so that two currents will be, if we add them together, that will equal to 0.4642 amperes, right, like this. Then again we can apply the Norton's theorem also in here, right. So if we can remember from the previous one what we have done, yeah, we can replace this one by like this, right. So I have done same example previously, right, same example previously. So here this will be 6 over 2 and this will be 2, this will be 4 over 3 and this will be 3, right. So like that we can calculate, and after we calculate the total current in here, again it is equal to like the previous one, right. You will get 1303, and the resistance also you can calculate, right. Yes, like that. In Norton's theorem, right. So like in the previous one, what we have done is actually like using that Norton's and the Millman's theorem, right. So like I have shown you in here, you can do the same in here as well, right. So therefore so this circuit will simplify to like this, right. So this will become 1303, this will become 605. This is actually the resistance, right. So after we connect it like 1303 and 605 to this 10, right, again we know the current going in here, it is 13 over 3, right. Then we can use the current divider, so that means the current going in this branch is proportional to 6 over 5 divided by 10 plus 6 over 5, right, into the total current, right. And the current going in this branch is equal to this value multiplied by 10 divided by 10 plus 6 over 5, right. So like that we can calculate. So you will get IL, the current going through this 10 ohms resistor as 0.4642 amperes, like the same answer that we got previously. Right. Okay, so question number 4. For the network shown in figure Q4, apply Norton's theorem to determine the current I20 flowing through the 20 ohm resistor. That means this one, right? The 20 ohm resistor connected between points A and B is removed. Yes, first you have to remove. Determine the value of the new resistor required between A and B to allow maximum power transfer from the rest of the network. Okay. Okay, so if we going into the basics of the Norton, so you know that we have to short circuit the output, right? You are short circuit the output, right? So then the series resistor can be ignored because the current flows through the resistor is just equal to the current source supply. So series resistor will work as short circuit, right? That means when there's a current comes here, right? So there's a junction, right? So when there's current comes here, this current will not go through this resistor, right? Why? Because there's a resistance, and here it has a clear path without a resistance, this path. So therefore there won't be any current flowing through this, right? So therefore the current going in here, it is actually equal to this current, which is equal to 1 ampere, right? Then in order to find the RNO, the what we call the Norton's resistance, right? So we have to open circuit the current sources and short circuit the voltage sources, right? Short circuit the voltage sources and open circuit the current sources, right? So then you will get then you can calculate the resistance. So you can see that after we open circuit these two, right, when we look at from here, right, when we look at from here, you will see only because we are interested in from this side, because that is where we are going to replace with the Norton. So therefore we will see only 10 ohms, right? So therefore Norton's equivalent resistance, it is equal to 10 ohms, right? So this is equal to 1 ampere and this is equal to 10 ohms, and here we have connected it like this. Again, by using the current divider, right, you can calculate I20, which is equal to INO into 10 divided by 10 plus 30, sorry, 10 plus 20, right, because this is 20 10 plus 20. So you will get 0.33 amperes, right? So the current going through this one is 0.33 amperes, right? And you may know from theory, right, the maximum power transfer, right, it will occur when the RL is equal to the load. Now our load is what? Our load is this 20 ohms, right? This 20 ohms, right? So that is what we have here, right? 20 ohms means the load that we have here, right? So therefore it asks to determine the value of new resistor required between A and B to allow maximum power transfer. So when RL is equal to the Norton's equivalent resistance, or the series parallel resistor that we have in here, at that time only it will have the maximum power transfer, right? So therefore when we have current in here and when you have RNO as 10 ohms, so this load should be, RL should be 10 ohms in order to have the maximum power transfer, right? And then we can find the maximum power dissipation. How to find the maximum power dissipation? So here you can see now we have 1 ampere. So since these two resistance are equal, so therefore you will get 0.5 amperes going through this one and 0.5 amperes going through this one after you apply the current divider, right? So the power dissipation in here is, so you know, P, it is equal to I squared into R, right? So what is that current? That current is this current, right? 0.5 squared into 10, 0.25 into 10, that is equal to 2.5 volts. So that is the maximum power dissipation, right? Maximum power dissipation. Okay, so like that we can do the calculation. So like this we can get the answers. Okay, so that's all on tutorial number 2.